Hampshire, England. February 1944. The howl of a Rolls-Royce Griffon engine shattered the morning calm across Boscombe Down airfield. Inside the cockpit of Spitfire serial number JF321, test pilot squadron leader Geoffrey Quill fought a battle that had nothing to do with enemy aircraft. His right leg trembled from the constant pressure on the rudder pedal, sweat beading on his forehead despite the bitter cold at 8,000 feet. The aircraft wanted to roll violently to the left, an invisible force trying to tear the nose away from level flight. Below him, engineers watched through binoculars, knowing that Britain's newest fighter had a fatal flaw that threatened to ground the entire program. The problem was brutally simple. Rolls-Royce had created a monster. The new Griffon 61 engine generated 2,050 horsepower, nearly double the output of the legendary Merlin engines that had powered earlier Spitfires through the Battle of Britain. That raw power should have made these late-war Spitfires the fastest fighters in the sky, capable of hunting down anything the Luftwaffe could field. Instead, the massive torque reaction from the spinning propeller transformed the beloved Spitfire into something pilots dreaded to fly. Every revolution of the five-bladed propeller generated a rotational force that tried to spin the entire airframe in the opposite direction. Physics didn't negotiate, and Newton's third law was turning Britain's most famous fighter into a dangerous beast that killed with indifference to the pilot's skill. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Joseph Smith sat in his office at Supermarine's Southampton Works, surrounded by technical drawings that represented months of failed solutions. At 47, Smith carried the weight of the Spitfire's entire future on his shoulders. He had inherited this burden in 1937, when R.J. Mitchell, the Spitfire's original designer, had died of cancer at just 42 years old. Mitchell had created the elegant elliptical wing and the graceful lines that made the Spitfire a legend. But it was Smith who had kept the design alive through constant evolution, transforming Mitchell's original vision into more than 20 distinct variants that adapted to every challenge the war threw at them. Now, in early 1944, that evolution had hit a wall that brute force engineering couldn't break through. The numbers told a grim story. At 350 miles per hour, Griffon-powered Spitfires required constant, aggressive rudder input just to maintain level flight. Pilots reported that the aircraft wanted to roll so violently that combat maneuvering became nearly impossible. At 400 miles per hour, the forces were so extreme that most pilots simply couldn't hold the aircraft straight. Aircraft production had invested millions of pounds developing the Griffon engine specifically to give Britain air superiority over Western Europe for the anticipated invasion. They had redesigned the Spitfire's airframe to accommodate the larger, heavier engine. They had expanded production facilities and trained thousands of workers to build these advanced fighters. But none of it mattered if pilots couldn't actually fly the damn things in combat. Smith's colleagues at Supermarine had tried every conventional solution. They increased rudder size, adding drag and weight without solving the fundamental problem. They modified engine mounts to reduce torque transmission, which weakened the airframe structure. They adjusted propeller blade angles, which helped marginally but created new problems with efficiency and vibration. Every fix addressed symptoms while the disease continued to kill. The engineering team was running out of ideas, and more critically, running out of time. German. Intelligence reports indicated that Messerschmitt was developing high-speed variants of their May 262 jet fighter. Focke-Wulf continued refining their high-altitude TAR-152 series. The technological race was accelerating, and Britain's most advanced piston-engined fighter was crippled by a problem that seemed to have no solution. 15 miles away, at the Rotol Propeller Works in Gloucester, a small team of engineers were pursuing an idea so unconventional that most aviation experts had dismissed it as mechanically impossible. Rotol had been formed in 1937, when the British government, recognising the approaching war, forced Rolls-Royce and Bristol Motors to pool their propeller expertise into a single company. The name itself was a merger. Roe from Rolls-Royce, Toll from Bristol, The company had earned a reputation for producing reliable variable pitch propellers that gave Spitfires and Hurricanes a crucial advantage during the Battle of Britain. But now they were proposing something that violated every principle of simplicity and proven reliability that had served British aviation so well. The concept was called contra-rotating propellers. Two separate propellers, mounted on the same shaft but spinning in opposite directions. The forward propeller would rotate clockwise, the rear propeller counterclockwise. The opposing rotations would cancel out the torque reaction that was crippling the Griffon-powered Spitfires. In theory, the system was elegant. In practice, it required engineering precision that pushed British manufacturing capabilities to their absolute limits. The technical challenges were staggering. A complex planetary gearbox would have to drive both propellers from a single engine output, adding at least 200 pounds of weight to an aircraft already straining the limits of its structural design. Each propeller would need individual pitch control, synchronized through a mechanism that had to work flawlessly under the enormous stresses of combat maneuvering. The entire assembly would have to be balanced to tolerances measured in fractions of ounces. Any imbalance at high rotational speeds would create vibrations that could literally shake the aircraft apart, and all of this complexity had to be reliable enough for mass production, field maintenance, and the brutal realities of wartime operations, where mechanics worked in freezing mud with inadequate tools and constant pressure to keep aircraft flying. When Rotol engineers first presented detailed drawings to Joseph Smith and his team at Supermarine in late 1943, the response was overwhelmingly skeptical. Senior aeronautical engineers who had spent decades simplifying aircraft designs looked at the contra-rotating system and saw a mechanical nightmare. The Ministry of Aircraft Production's technical staff wrote scathing reports about adding unnecessary complexity when proven reliable solutions were desperately needed. Test. Pilots who had survived years of combat flying expressed doubt that such a complicated system could be maintained under operational conditions. But Smith saw something different in those drawings. He understood that the Griffon engine's torque problem wasn't going to be solved by incremental improvements to existing designs. The laws of physics were absolute, and at 2,000 horsepower, those laws made conventional single-propeller configurations fundamentally unstable. The contra-rotating system didn't fight physics, it harnessed physics. The opposing rotational forces would cancel each other out completely, eliminating torque reaction while actually improving propeller efficiency. Calculations suggested a 15% increase in thrust compared to a conventional propeller absorbing the same power. More importantly, the Spitfire would finally be flyable at its full performance envelope. The autumn rains of 1943 hammered against the windows of Supermarine's design office as Smith made his decision. The contra-rotating propeller project would move forward, despite the skepticism, despite the technical challenges, despite the enormous risk of failure, because the alternative was worse. Without a solution to the torque problem, the Griffon-powered Spitfire program would fail. British air superiority over Europe would be compromised, and thousands of pounds, millions of man-hours, and Britain's most famous fighter would be relegated to footnotes in aviation history. Smith called a meeting with Rotol's chief engineers for early December. The agenda was simple but audacious. Design, manufacture, and test a working contra-rotating propeller system within 6 months. It was a timeline that seemed impossible, but then again, Britain had been doing impossible things since Dunkirk. The question wasn't whether they could do it. The question was whether they could do it before Germany's new fighters made the entire Spitfire program obsolete. The December morning of 1943 brought Joseph Smith to Rotol's manufacturing facility in Gloucester, where the scale of the engineering challenge became brutally apparent. In a cavernous workshop that smelled of machine oil and wood shavings, engineers had assembled a prototype gearbox that looked more like clockwork from a cathedral than aircraft machinery. 2 concentric shafts nested inside each other, driven by a 2-stage planetary gear train with reduction ratios calculated to microscopic precision. The forward propeller would spin at 1,825 revolutions per minute, the rear propeller at 1,475. The differential speeds were critical, carefully chosen to cancel torque, while maximizing thrust efficiency across the Spitfire's entire speed range. Each component had to be machined to tolerances normally reserved for precision instruments. The gears couldn't deviate more than 1/1000th of an inch from specification, or the entire system would vibrate itself to pieces at operational speeds. The propeller blades, each one handcrafted from compressed wood laminate, had to be balanced within half an ounce of each other. A tiny imperfection in one blade would create harmonic vibrations that amplified exponentially as rotational speed increased. Smith watched as technicians used specialized equipment to measure blade weight down to individual grams, shaving microscopic amounts of material to achieve perfect balance. The technical complexity extended beyond just the mechanical components. Each propeller needed independent pitch control, allowing pilots to adjust blade angles for optimal performance at different speeds and altitudes. But with two propellers spinning in opposite directions, the pitch control mechanism had to work through what engineers called a translational bearing, a component that had to transmit hydraulic pressure and control signals through rotating shafts while maintaining perfect synchronization. If this bearing failed, one propeller would lose pitch control while continuing to spin at 1500 revolutions per minute. The result would be catastrophic, possibly tearing the entire assembly off the front of the aircraft. Rotol's chief engineer, a methodical Scotsman named Robert Morrison, walked Smith through the assembly process with the grim efficiency of a man who understood exactly how many things could go wrong. "The gearbox alone weighs 193 pounds, Morrison explained, tapping the massive assembly with a wrench. "Add both propeller assemblies, and we're looking at 220 pounds of additional weight compared to a standard 5-blade unit. That's the equivalent of carrying an extra crewman, except this crewman is mounted on the nose, where it affects the aircraft's center of gravity." Smith had anticipated the weight penalty, but hearing the actual numbers brought the challenge into sharp focus. The Spitfire's performance depended on a carefully calculated balance between power, weight, and aerodynamic efficiency. Adding 200 pounds to the nose would shift the center of gravity forward, requiring additional ballast in the tail to maintain proper trim. That meant even more weight, which would affect climb rate, maneuverability, and range. The contra-rotating system would have to deliver exceptional performance just to overcome its own mass. By February 1944, 6 weeks after Smith's initial meeting with Rotol engineers, the first complete contra-rotating propeller assembly was ready for installation. The test aircraft was Spitfire Mark 8, serial number JF321, a converted airframe that had already been fitted with a Griffon 61 engine for earlier trials. The installation took 3 days of careful work, with engineers constantly checking alignment and clearances. The two propellers, each 11 feet in diameter, created a visual effect that seemed to challenge the fundamental laws of aviation engineering. When the aircraft was finally rolled out of the hangar, it looked like something from a science fiction story. Ground testing began immediately. The Griffin engine fired with its characteristic deep rumble, but the sound was immediately altered by the contra-rotating propellers into something entirely new. Instead of the familiar rhythmic pulse of a single propeller, the twin assemblies created a complex harmonic that seemed to vibrate through the entire airframe. Engineers measured oil pressures, gearbox temperatures, and propeller synchronization, searching for any sign of the mechanical failures that skeptics had predicted. For the first few hours of testing, everything performed exactly as calculated. The gearbox maintained stable temperatures. Oil pressure stayed at 60 pounds per square inch throughout the power range. The propellers rotated in perfect opposition, their different speeds creating the cancelling effect that theory predicted. But ground testing meant nothing until the system proved itself in actual flight. On February 23, 1944, squadron leader Geoffrey Quill strapped himself into the modified Spitfire for what everyone understood would be the crucial test. Quill was one of Britain's most experienced test pilots, with nearly 800 hours in various Spitfire variants. He had tested every major modification to the aircraft since 1938, including the original Griffin installations that had revealed the torque problem. If anyone could evaluate the contra-rotating system fairly, It was Quill. But even he approached the aircraft with visible caution. The takeoff at 9:32 revealed the system's most immediate benefit. For the first time in months of testing Griffin-powered Spitfires, the aircraft tracked straight down the runway centerline without constant rudder correction. The contra-rotating propellers eliminated the familiar left turning, a tendency that every Spitfire pilot had learned to counteract. Liftoff occurred at 85 miles per hour, exactly as predicted. But as Quill climbed through 5,000 feet, he immediately noticed something wrong. The aircraft felt sluggish. Where a standard Griffin Spitfire could climb at 2,000 feet per minute using 75% power, Quill found himself advancing the throttle to nearly full power just to maintain the same climb rate. The additional weight of the contra-rotating system was affecting performance more severely than Smith's calculations had suggested. By the time he reached 6,000 feet, Quill was using full military power for what should have been routine climb performance. The fuel consumption at these power settings would reduce the aircraft's already limited range to completely unacceptable levels. But when Quill leveled off and reduced power to cruising settings, he discovered something remarkable. Despite the climb performance issues, the aircraft felt extraordinarily stable in level flight. The elimination of torque reaction had transformed the Spitfire's handling characteristics in ways that went far beyond simple directional control. At 300 miles per hour, the aircraft that had previously tried to roll uncontrollably now flew with steady precision. Quill experimented with gentle turns, steep banks, and rapid direction changes, finding that the Mark 21 responded with an agility that seemed impossible for such a large, powerful fighter. Boscombe Control, this is Test 27, Quill radioed. Handling below 300 is exceptional. The torque cancellation is complete. But I'm experiencing higher than expected power requirements for normal climb, requesting clearance to test high-speed envelope. The response crackled through his headphones immediately. Test 27, you're cleared for speed testing. Exercise extreme caution. Quill advanced the throttle toward maximum power, and the aircraft's performance became genuinely alarming. Instead of accelerating smoothly toward its theoretical top speed of 470 miles per hour, the Spitfire began to vibrate with increasing intensity. At 370 miles per hour, the entire airframe shook so violently that Quill could barely read his instruments. The contra-rotating propellers, designed to operate in perfect harmony, seemed to be creating destructive interference patterns that threatened to tear the aircraft apart. Boscombe Control, Test 27 experiencing severe vibration above 370. I'm reducing power and returning to base for emergency landing. The flight had lasted 43 minutes. Quill's face was grim as he climbed from the cockpit, knowing that Joseph Smith's revolutionary design had just failed its first crucial test. The contra-rotating propellers worked perfectly at eliminating torque reaction during takeoff and low-speed flight. But they had introduced new problems that were potentially more dangerous than the original difficulties with the Griffon engine. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The emergency meeting in Hangar 7 at Boscombe Down felt more like a tribunal than an engineering conference. Air Commodore Ralph Sawley had driven down from London immediately upon receiving the preliminary flight report, and his presence transformed what should have been a technical debriefing into something resembling a court-martial. Around him sat engineers, test pilots, and ministry officials whose expressions ranged from disappointment to barely concealed anger. The modified Spitfire sat silent behind them, its contra-rotating propellers now motionless but still radiating an aura of mechanical menace. Squadron Leader Quill, Sawley began, his voice carrying the weight of institutional authority. Please give us your complete assessment of the aircraft's performance characteristics during today's test flight. Quill stood at attention, though his flight suit still bore sweat stains from wrestling with an aircraft that had nearly shaken itself apart. Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and low-speed flight. The aircraft tracked straight down the runway without rudder input, and handling below 300 miles per hour was exceptional. possibly the best I've experienced in any Spitfire variant. A murmur of surprise rippled through the assembled engineers. Despite the flight's dramatic conclusion, Quill's initial assessment suggested that Smith's basic concept had succeeded in solving the Griffon engine's primary problem. However, Quill continued, his tone becoming more somber. Above 370 miles per hour, the aircraft experienced severe vibrations that made further speed increases impossible. The entire airframe shook so violently that I feared structural failure. Additionally, climb performance was significantly degraded. We required nearly full power to achieve climb rates that should have been possible at 75% throttle. Smith felt the weight of failure settling on his shoulders. 6 months of calculations, manufacturing precision, and professional reputation had produced an aircraft that performed brilliantly at low speeds, but became uncontrollable precisely when maximum performance was needed most. The irony was bitter. He had solved the torque problem only to create vibration issues that were potentially more dangerous than the original difficulties. Chief Engineer Morrison consulted his clipboard of technical data, searching for explanations that might salvage something from the disaster. Our ground-running tests showed harmonic vibrations at specific engine speeds, but nothing approaching the severity squadron leader Quill experienced in flight. The aerodynamic loads at high speeds seemed to be exciting resonances in the propeller system that we didn't anticipate. The room fell into a tense silence as everyone absorbed the implications. The contra-rotating system had revealed a fundamental problem that ground testing couldn't predict. At high air speeds, the interaction between two propellers spinning in opposite directions created complex aerodynamic phenomena that laboratory calculations had completely missed. The propeller tip vortices, the spiraling air masses shed by each blade, were creating destructive interference patterns that amplified vibrations to dangerous levels. Sawley's expression suggested he was already calculating the political consequences of another failed aircraft modification program. "The question now," he said grimly, "is whether these problems can be solved within a reasonable time frame, or whether we should abandon this approach entirely and focus on conventional solutions to the Griffin's torque issues." Smith's engineering instincts refused to accept defeat without exploring every possible solution. "Sir, I believe the vibration problems can be resolved through modifications to the propeller blade design and gearbox timing. The fundamental concept remains sound. We simply need to eliminate the aerodynamic interference that's causing the destructive resonance." Test pilot Quill, despite having risked his life in the morning's flight, found himself unexpectedly supporting Smith's position. "With respect, sir, the aircraft's handling below 370 miles per hour was remarkable. If Mr. Smith can solve the high-speed vibration issue, we could have an aircraft that combines the Griffin's power with handling characteristics that exceed any fighter currently in service." Sawley consulted his notes, weighing the competing demands of technical perfectionism against operational urgency. Allied intelligence reports indicated that German aircraft manufacturers were rapidly developing new high-performance fighters. The invasion of Western Europe, still months away but already consuming enormous planning resources, would require absolute air superiority over the battlefield. "Mr. Smith," Sawley said finally, "you have one more opportunity to prove your system. But understand that this represents the absolute limit of our patience with experimental approaches. If the second test flight fails to demonstrate clear improvements, we will abandon the contra-rotating propeller program entirely and focus our resources on conventional torque reduction methods." Joseph Smith spent the next 3 weeks in a state of controlled desperation that bordered on obsession. Sleep came in brief intervals between calculations, each night interrupted by sudden realizations about propeller blade geometry or gearbox resonance frequencies. The problem haunted him because the solution seemed tantalizingly close. The contra-rotating system worked perfectly at low speeds, proving the fundamental concept was sound. High-speed vibrations weren't a failure of engineering principles. They were a failure to understand the complex aerodynamics of two propellers operating in close proximity at near-supersonic tip speeds. The breakthrough came during a late-night session with Rotol's senior aerodynamicist, a brilliant but temperamental engineer named David Wright. Wright had been analyzing the vibration data from Quill's test flight, plotting the frequency patterns against propeller rotational speeds. What he discovered was both elegant and frustrating in its simplicity. The vibrations occurred because the original gear ratios created a harmonic relationship between the two propellers that amplified at specific speeds. At 370 miles per hour, with the forward propeller spinning at 1,825 revolutions per minute and the rear at 1,475, the blade passage frequencies created a resonance that excited the aircraft's natural structural frequencies. "It's like striking a tuning fork," Wright explained, sketching frequency diagrams on a chalkboard covered with weeks of accumulated calculations. The propellers are generating sound waves and pressure pulses at frequencies that match the airframe's resonant modes. At high speed, those pulses amplify each other instead of cancelling out. But if we change the speed differential between the propellers, we can shift the harmonic frequencies away from the critical resonance points. The solution required recalculating the entire gearbox system. Instead of the original 1825 and 1475 revolutions per minute, the new configuration would run at 1700 and 1500 revolutions per minute, respectively. The closer speed differential would shift the critical resonance frequencies away from the aircraft's normal operating range, while maintaining the torque-cancelling effect that made the system valuable. Additionally, Smith's team modified the blade twist distribution on both propellers, reducing the aggressive angle changes near the tips that contributed to vortex formation. Each blade now featured a more gradual transition from root to tip, designed to minimize the aerodynamic interference that had created destructive vibrations. The modifications required completely rebuilding the gearbox, a process that consumed 2 weeks of intensive machine shop work. Each gear had to be recut to new specifications, then heat-treated, ground, and polished to tolerances, measured in thousandths of an inch. The propeller blades underwent even more painstaking modification, with craftsmen hand-finishing each one to create the new twist distribution. Every blade had to be rebalanced after modification, a process that involved removing microscopic amounts of material while constantly checking weight distribution. By mid-March 1944, the modified contra-rotating assembly was ready for installation, but the pressure on Smith and his team was immense. This was their final chance. The morning of March 18, 1944, brought clear skies and calm winds to Boscombe Down, conditions that seemed almost too perfect for what everyone understood would be the definitive test. Squadron leader Quill approached the modified Spitfire with cautious optimism tempered by vivid memories of his previous flight's violent conclusion. The aircraft looked identical from a distance, but close inspection revealed the subtle changes that might transform it from a dangerous experiment into a revolutionary weapon. Chief Engineer Morrison supervised the pre-flight inspection with nervous energy that infected everyone in the hangar. "The gearbox modifications tested perfectly during ground running," he reported to Quill. "We maintained stable operation through the entire power range without the harmonic vibrations that plagued the original system. Oil temperatures stayed within normal limits, and the new gear ratios eliminated the resonance frequencies we identified during failure analysis." Air Commodore Sawley had returned from London specifically to witness this second test, bringing with him a sense of institutional finality that affected everyone present. The Ministry of Aircraft Production could not afford to continue experimental programs indefinitely, particularly when conventional aircraft were desperately needed for the anticipated invasion of Europe. This flight would determine not only the fate of Smith's propeller system, but potentially the future direction of British fighter development. At precisely 10:15, Quill fired the Rolls-Royce Griffon engine and immediately noticed differences from the previous test. The sound was subtly different, still the complex harmonic created by contra-rotating propellers but somehow more controlled, less aggressive in its mechanical resonance. The engine instruments showed normal readings as he advanced power for taxi, and the aircraft tracked, straight without the slight vibration that had characterized the original system even during ground operations. Takeoff at 10:28 revealed the most dramatic improvement. Where the previous flight had required nearly full throttle to achieve acceptable climb performance, the modified aircraft now ascended at 2,000 feet per minute, using only 80% power. The revised propeller geometry had apparently eliminated much of the aerodynamic inefficiency that had plagued the original design, allowing the Griffin engine's full power to translate into actual aircraft performance. Boscombe Control, Test 27 climbing through 8,000 feet, Quill radioed, his voice carrying cautious excitement. Climb performance is significantly improved over the previous test. Handling characteristics remain excellent. Requesting clearance to test speed envelope. The response came immediately. Test 27, you're cleared for speed testing. Exercise extreme caution, approaching previous problem areas. Quill leveled the Spitfire at 10,000 feet and began his cautious exploration of the speed range that had nearly killed him 3 weeks earlier. At 300 miles per hour, the aircraft flew with the smooth precision he remembered from the first test. At 350 miles per hour, still no unusual vibrations or handling anomalies. As the airspeed indicator crept past 370 miles per hour, the speed at which the original system had become uncontrollable, Quill held his breath and waited for the violent shaking that had forced his emergency return. Instead, the Spitfire continued to accelerate smoothly. At 400 miles per hour, the aircraft felt more stable than most fighters at half that speed. The elimination of torque reaction combined with the resolved vibration issues had created something unprecedented in aviation. A high-powered fighter that actually became more controllable as it approached its maximum performance envelope. Boscombe Control, Test 27 has achieved 410 miles per hour with no adverse handling characteristics, Quill reported, his voice now carrying genuine excitement rather than caution. The aircraft is completely stable and responsive. This is remarkable performance. From the control tower, Smith watched through binoculars as his modified Spitfire carved precise turns against the blue Hampshire sky, the contra-rotating propellers transforming the massive power of the Griffin engine into speed and agility that seemed to defy the laws of aviation physics. The sight vindicated not only months of technical work, but his fundamental belief that conventional approaches were insufficient for the challenges of modern warfare. Quill continued testing for another 25 minutes, exploring every aspect of the aircraft's performance envelope. High-speed dives revealed that the Spitfire could exceed 450 miles per hour in a controlled descent without developing the compressibility problems that affected many high-performance fighters. Tight turns at maximum power demonstrated handling that combined the agility of earlier Spitfire variants with the raw performance of the Griffin engine. When he landed at 11:32, Quill's expression carried the weight of professional expertise earned through years of combat flying. "Gentlemen," Quill announced as he climbed from the cockpit, removing his flying helmet and looking directly at Smith, "what you have created is not simply an improved Spitfire. This is the finest fighter aircraft I have ever flown. The combination of speed, handling, and controllability exceeds anything in current service with any air force in the world." Air Commodore Sawley approached Smith with an expression that had transformed from skeptical authority to grudging admiration. "Mr. Smith," Sawley said formally, "I believe congratulations are in order. Your contra-rotating propeller system has exceeded our most optimistic performance predictions. The question now is how quickly we can begin production modifications for operational squadrons." But even as Smith savoured the moment of vindication, he understood that proving the system worked was only the beginning. Transforming experimental success into battlefield advantage would require manufacturing precision, pilot training, and logistical support on a scale that would test Britain's wartime industrial capacity to its limits. The contra-rotating gearbox demanded tolerances that only specialized machine shops could achieve. Each propeller assembly required hours of hand finishing and balancing that couldn't be easily replicated on production lines. Field maintenance would require training mechanics to work on systems far more complex than anything they had encountered. By mid-1944, as Allied forces prepared for the invasion of Normandy. Several Spitfire variants had been fitted with contra-rotating propellers for extended service trials. Mark 21, serial number LA215, was delivered to the Air Fighting Development Unit at Tangmere in May 1945 for comprehensive evaluation. Pilots flew 71 hours of trials, testing the aircraft in every conceivable combat scenario. Their reports were unanimous and enthusiastic. The contra-rotating propeller eliminated the need for constant rudder trim adjustments, making the aircraft an exceptional gun platform for both air-to-air and air-to-ground firing. Pilots could hold the gun sight on target even when enemy aircraft took violent, evasive action, something that had been extremely difficult with standard propeller configurations. But the timing was cruel. By the time the contra-rotating system had been perfected and production methods developed, the war in Europe was ending. The desperate urgency that had driven the program's development evaporated with Germany's surrender in May 1945. The Royal Air Force suddenly found itself with thousands of conventional Spitfires that performed adequately for occupation duties and emerging jet fighters that promised to make piston-engined aircraft obsolete within years. Only one production variant received contra-rotating propellers in significant numbers. The Seafire 47, the naval version designed for carrier operations, was fitted with the system specifically to solve the Spitfire's long-standing problem with deck landings. The short undercarriage and powerful engine had made carrier operations extremely challenging, with numerous accidents caused by torque-induced ground loops during landing. The contra-rotating propellers transformed the Seafire into a manageable carrier aircraft, and these naval fighters saw operational service in Malaya and Korea in the late 1940s and early 1950s. The broader impact of Smith's work extended far beyond the limited production numbers. The engineering knowledge gained from developing reliable contra-rotating gearboxes influenced post-war turboprop designs. When Britain developed the Fairey Gannet anti-submarine aircraft and the Westland Wyvern strike fighter in the 1950s, both used contra-rotating propellers based on principles proven with the Spitfire. The Soviet Union, working with captured German engineers, developed the massive contra-rotating propellers for the Tupolev Tu-95 Bear bomber, which became the fastest propeller-driven aircraft ever to enter operational service. Joseph Smith continued working at Supermarine after the war, overseeing the transition from piston engines to jets. He designed the Supermarine Attacker, one of Britain's first operational jet fighters, and the experimental Swift, which briefly held the world airspeed record in 1953. But Smith never forgot the contra-rotating Spitfire project, the moment when his refusal to accept conventional limitations had created something genuinely revolutionary. In 1956, Joseph Smith died at the age of 59, his contributions to British aviation overshadowed by the more famous R.J. Mitchell, but no less significant. The story of the contra-rotating Spitfire reveals a profound truth about wartime innovation. Success isn't measured solely by production numbers or combat victories. Sometimes the greatest achievements are the problems solved, the barriers broken, the moments when engineers refuse to accept that something can't be done simply because it's never been done before. Smith's stupid idea, the mechanically complex contra-rotating propeller system that colleagues dismissed as impractical, proved that sometimes the most elegant solution is the one that embraces complexity rather than avoiding it. Today, when aviation enthusiasts watch restored Spitfires perform at air shows, most are unaware that a handful of these aircraft once flew with contra-rotating propellers that transformed them into the ultimate expression of piston-engined fighter design. The distinctive sound of opposing propellers cutting through the air has largely been forgotten, replaced by the roar of jets that made such mechanical complexity obsolete. But for a brief moment in 1944, Joseph Smith and his team at Supermarine and Rotol proved that the limits of aviation technology were defined not by what seemed practical, but by what physics would allow. The Griffin engine that created the torque problem had been designed to give Britain air superiority. The contra-rotating propellers that solved it represented something more fundamental: the human capacity to transform obstacles into opportunities through engineering, courage, and technical brilliance. In the skies above Hampshire, as Squadron Leader Quill pushed that modified Spitfire past 400 miles per hour without a single wobble, every revolution of those opposing propellers proved that sometimes the stupidest ideas become the most revolutionary solutions when engineers dare to challenge conventional wisdom. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.